Hello, everyone, and welcome to December's meeting. Our speaker is Dr. Eliot Quataert from Princeton University. Originally from Santa Monica, California, Eliot obtained an undergraduate degree in physics from MIT and a PhD in astronomy from Harvard University. He is an elected member of the National Academy of Science and the American Academy of Arts and Sciences. Eliot's multifaceted research has made him a well-respected colleague among his peers. His interest in discussing topics with students has made him one of the most sought-after professors on the undergraduate and graduate level. Eliot's enthusiasm has led him to become a principal spokesman for Princeton's public outreach programs. In addition to astrophysics, Eliot also enjoys hiking, cooking, reading, growing his own vegetables, and being a photographer of nature. So please welcome Eliot as he shows us one of the most photogenic wonders of the universe.
Thank you, Pat. So let's see. Going to set this up. All right. Can everybody see my screen okay and hear me okay?
Yes.
Okay, hold on. Let me just get this out of the way for myself. Okay. Well, it's a pleasure to be talking to you tonight. Sorry, I can't be there in person. So what I'd like to tell you a little bit about tonight is how, despite their name and despite sort of the definition of black holes as being objects from which nothing can escape, they actually produce some of the brightest sources of light that we see in the sky. And we've actually been able to take pictures of what it looks like very, very close to the point of no return, what's called the event horizon, the region from within which nothing can get out. So I always like to start talks like this by just giving a little bit of context. So I think you probably think of astronomers as, maybe especially professional astronomers, as people who could tell you what's up in the night sky, what Jupiter is doing, what Saturn's moons are doing, what Saturn's rings are doing, who knows the constellations, who knows how to work telescopes. But that's really not the kind of astronomer that I am. So really, astronomers come in a few different varieties. There are people who do the observations, people who build the telescopes, develop the detectors that sit behind the mirrors on telescopes. And then there are people who do more of the theory, who use math and physics to interpret what we see in the sky, to make sense out of the observations, and to build a theoretical framework for understanding the universe that we live in. And that's the kind of astronomy that I do. So my background is really more in the math and physics. Had I given the what's up in the night sky intro a few minutes ago, it would have been deeply embarrassing for me, since that's really not my area of expertise. So rather than, telescopes, binoculars, CCDs being my tools are much more calculators, pencil and paper, iPads, some of the biggest supercomputers in the world. So I really do everything from calculations that I can do on the laptop that I'm sharing my screen with you tonight on, to calculations on supercomputers, in the US, in Europe, et cetera, and sort of everything in between. And most of what I do is theoretical modeling predictions of new things to be observed or interpretation of of recently discovered observations. And so I'll tell you a little bit about sort of my role in some of the work that I've done with my group in the context of understanding what black holes look like. So one of the great things about talking about this subject, talking about black holes, and by the way, just a quick note, I can't see the chat on Zoom. So if anything comes up and you want to get my attention, just please speak up. Don't rely on the chat because the way my screen is set up right now, I can't see that. Okay. So as I was saying, one of the great things about talking about black holes is that they are one of the topics in science that has permeated popular culture the most effectively. There are many movies that feature black holes. There are many episodes of Star Trek that feature black holes. There's this graphic novel with a pseudo-zombie thingy here that had the name black holes, although really wasn't related to the science of black holes. Probably the most recent in the last decade or so large-scale popular manifestation of black holes in popular culture is the Christopher Nolan movie Interstellar, which was basically black holes played an essential role in almost all of the plot of the movie. This movie also stands out, if you don't know it, that the person on my right here, Kip Thorne, who is a physicist at Caltech, actually a Nobel Prize-winning physicist for his work on the discovery of gravitational waves with LIGO, a gravitational wave interferometer. He was actually the original screenwriter for the movie Interstellar and one of the producers. So the movie Interstellar is actually known also for being, I would say, in the scheme of Hollywood movies, it is unusually scientifically accurate. That doesn't mean that it's scientifically accurate. It just means it's closer to scientifically accurate than a randomly picked science fiction Hollywood movie would be because of Kip's key role in the development and production of the movie. So just to give you a sense of how much black holes are out there in popular culture, this is an Amazon search I did where you get 101,844 hits on black holes on Amazon. This includes some great movies, the original Disney movie Black Hole, a book by Neil deGrasse Tyson, Death by Black Holes, this graphic novel, Black Hole, that is the zombie-esque thing here, is actually the first hit on this particular search. Black holes show up in weird places in Amazon that you wouldn't expect, like healthcare and personal care. I'm not exactly sure what those are. Most of the hits are things you would expect, like movies or books having to do with science or science fiction. Now, there is a downside to black holes permeating popular culture the way they do, which is that it's sort of like the old game of telephone. As the information gets communicated from the scientists through to the screenwriters and eventually through to popular culture, there's a lot of errors that creep in along the way. And so part of what I'd like to do in telling you the story about the science of black holes is correct some of those misimpressions and tell you a little bit about our actual scientific understanding of black holes. And I'll try to do this through the lens of two questions. So one is, what are black holes? Namely, what do theoretical physicists like Einstein think black holes are? And then the second question is, do those objects actually exist in nature? Are they out there in the universe? How can we find them and study them? And these are separate questions, right? Theoretical physicists like myself are very creative. Most of the ideas we come up with are wrong in the sense that they might be good physics ideas, but they aren't necessarily actually realized out there in the universe. And so we always have to go and test our theories, and that's sort of the more observational part of the talk of how do we find and study black holes. So the story of black holes is really a story about gravity. Gravity is the most important force on large scales in the universe. It's the force that holds everything from stars to galaxies to planets like Jupiter. It's the force that holds all of those objects together. It relentlessly attracts everything in the universe. So if you take an object like the sun or the earth, there's this relentless inward pull of gravity that basically wants every object in the universe to collapse in on itself due to the force of gravity. And in objects like galaxies or stars or planets, there's something that is pushing out, keeping gravity at bay, at least for a while. And in things like the sun or planets like Jupiter, that force pushing out, keeping gravity at bay, is pressure. It's the fact that the interior of the planet or the star is hotter than it is near the surface. And that hot interior pushes out on the cooler exterior and stops the inward collapse that gravity would want to produce. And in a star like the sun, that balance between pressure and gravity lasts for something like 10 billion years. And in fact, the interior of the sun is kept hot because of nuclear fusion of hydrogen in the center of the sun. But we know from our everyday experience here on Earth that this balance between pressure and gravity on the Earth or in the sun isn't absolute. We can overcome the gravitational clutches of the Earth. We have done that successfully. We have launched rockets off the surface of the Earth that have actually traveled out of the solar system in the case of the Voyager satellites, or in the case of most satellites, they've traveled into orbit around the Earth. And in physics, we know that for any object, there's sort of a critical speed of how fast something has to go launched from the surface of that object to escape the gravitational clutches of the object. That speed in physics is known as the escape speed. It depends on the mass of the object and the radius of the object, because those two things, how much stuff there is and how big something is, determine the strength of gravity. The more mass there is, the stronger gravity is, the faster you need to throw a rocket or launch a rocket to escape the gravitational clutches of an object. And similarly, the smaller an object is, the smaller its radius is, the stronger its gravity is because things are closer together, gravity is stronger. And again, the faster a rocket would need to be launched to escape the gravitational clutches of an object. So in the case of the Earth, we need to launch rockets if it was one immediate thrust on the surface of the Earth. You would need to launch a rocket with a speed of about 11 kilometers a second, 27,000 miles an hour, to escape the gravity of the Earth. But the sun is much more massive than the Earth. Its gravity is much more stronger than the Earth. So all of those amazing rockets that we've built that have escaped the gravitational clutches of the Earth, if you tried to launch them from the surface of the Earth, well, the first problem is that all those rockets would burn up because the surface of the sun is much hotter than the surface of the Earth. But leaving that aside for a moment, the gravity of the sun is so strong that all of the rockets that we've developed would not be able to escape the gravitational clutches of the sun. They would just go up a tiny bit and come crashing back down into the surface of the sun. And so in physics, the way we say that is that the escape speed of the sun is about 50 times larger than that of the Earth. And so rockets would need to be launched at 600 kilometers a second or 1,000,000 miles an hour to escape the gravity of the sun. So this basic physics, gravity, how fast you need to go to escape the gravitational clutches of an object, this is physics that was developed basically by Isaac Newton in the late 1600s. And it was only a bit after that, actually, that the first inklings of what we now think of as black holes were developed in physics and astronomy. And this is due to two scientists about 100 years after Newton, John Michel and Pierre Laplace. Laplace is one of the most famous mathematicians who also did some physics. Michel was actually mostly a geologist who did a lot of work on earthquakes. And they both independently ask this incredibly brilliant question. And in fact, most of doing scientific research isn't about solving questions. It's about coming up with the really clever new question in the first place. And the questions that Michel and Laplace posed are actually some of the most profound ones in the history of astronomy and physics. So they knew already in the late 1700s that the speed of light was absolutely enormous, but it was finite. This was actually measured by Romer using observations of the moons of Jupiter undergoing eclipses and transits, where the moons go behind or in front of the surface of Jupiter. So Romer had measured the speed of light to be something like 1 billion miles an hour, about a foot per billionth of a second. So that's an extraordinarily large speed. That's so large that basically in all of our everyday experience, for practical purposes, it's as if the speed of light were infinite, but it's actually not. And Michel and Laplace knew that, so they asked a very simple question. What if you took Newton's idea of escape speed and applied it to light? What if you had a star that was so small that its escape speed were larger than the speed of light? And they coined these objects dark stars. And the idea that they put out there is maybe there were stars out there in the universe whose gravity was so strong that not even light could escape that object. And that would be a star we couldn't see, or what we now call black hole. And Michel and Laplace even combined Newton's theory for escape speed with Romer's measurement of the speed of light, and they estimated how big would one of these dark stars or black holes have to be. And what they concluded is that if you took the Earth, the entire mass of the Earth, you'd have to shrink it down to an object smaller than about a marble, about an inch big, to make an object so strong that light could not escape the gravity of that object. Or equivalently, because the sun's mass is much bigger, you'd have to take the sun and shrink it down to about the size of a city, a few miles big, in order to create a black hole or a dark star. And this size of an inch for a mass of the Earth or a mile for the mass of the sun is still basically the correct estimate for the size of what we now call the event horizon of a black hole. So this incredibly brilliant idea, one of these ideas that most scientists, including myself, will never have such an important idea in their lifetime, right? This idea languished actually for well over a century after Michel and Laplace came up with it. And the reason it languished is that Michel and Laplace cheated a little bit. Really, Newton's theory of gravity can't apply to light. It only applies to objects that have a finite mass, and light has energy, but not really mass. And it wasn't until Einstein came along and taught us that there's actually a relationship between energy and mass that we had a new theory that was sophisticated enough to give us our modern understanding of black holes. And that's Einstein's theories of relativity, developed in the early 1900s. And the basic idea of black holes in Einstein's theories of relativity shares many similarities to this Michel-Laplace notion that I explained to you. It's basically that the idea that if an object is small enough, gravity wins out over every other possible force in the universe. And gravity is so strong that the object, independent of what pressure is supporting it, if the object is small enough, gravity wins and the object collapses in on itself. And the object collapses to such a small region that nothing, not even light, can escape the gravitational clutches of the object. And in Einstein's theory of relativity, the size of a black hole is really fundamentally different from the size of any other object in astronomy. When we talk about the size of the Earth, we typically mean the surface, where it goes from being solid to gas, or maybe we mean something about the outer parts of the atmosphere of the Earth. But whatever we mean about the size of the Earth, there's something there. There is matter there at what we mean by the radius of the Earth. And that's not true in general for Einstein's theory of black holes. The size of a black hole in Einstein's theory of relativity is defined simply by information. Inside the event horizon, nothing traveling at the speed of light can get out. Outside the event horizon, information traveling at the speed of light can get out to a distant observer, but there's nothing actually at the event horizon itself. Because in Einstein's theory, all of the mass that makes up a black hole has collapsed in on the black hole to the very center of the black hole, to what we call the singularity, the sort of point where all of the mass gets compressed into a region so small that we're not even sure exactly what happens to matter in that tiny little region. Okay, so that's basically Einstein's idea of black holes in one slide. Next spring, I'll actually be teaching an entire class for non-scientists, so non-science majors on black holes, where we'll spend like 5 lectures fleshing out this one slide in a lot more detail. So this idea of the event horizon as being the point of no return inside of which nothing can escape, I think this gives rise to the single biggest misconception of black holes in popular culture that permeates sort of many, many facets of science fiction, books, movies, television shows, etc. And that is that black holes are sort of a cosmic vacuum cleaner that inevitably suck up everything around them. And that after this lecture, you're going to go home and have nightmares because you're going to worry that maybe we on Earth are going to get sucked into some black hole out there in the galaxy. And that is not true. And the reason it's not true is that far away from a black hole, Newton was right. Newton's theory of gravity is right. And so gravity, the gravity of a black hole far away from a black hole is really no different than the gravity of any other object. And so the Earth doesn't inevitably get sucked into the sun because of the gravity of the sun. Instead, the Earth orbits around the sun. And that's true for most objects interacting with black holes. They don't get sucked into the black hole. They just orbit around the black hole. And it's only if you're very close to the event horizon, technically, only if you're inside the event horizon, do you inevitably get sucked into the center and get ripped to shreds and destroyed as you approach the singularity. If you're outside the event horizon, far away from the event horizon, Newton's theory of gravity is basically right, and you would potentially orbit the black hole for a time much longer than the age of the universe. So to be very specific and give you an idea of what this means, if we took the sun and we just instantaneously got rid of the sun and we replaced it by a black hole that has the same mass as the sun, gravity would be the same. And so all the orbits of the planets, the asteroids, the moons around the planets, etc., those would be unchanged. So the solar system would not suddenly collapse into the black hole, just like it doesn't collapse into the sun. The only thing that would change is that there wouldn't be a nice source of heat keeping the solar system hot. So the Earth would get cold, everything would die. So that would be bad for lots of reasons, but it wouldn't be bad from the point of view of gravity. It would be bad from the point of view of light and heat and life and things like that. Okay. So that's basically the physics part of the story that I wanted to tell you. The rest of what I want to tell you is sort of the astronomy part of the story. Now that we have an idea of what black holes are, do they really exist? Are they actually out there in nature? And if so, how do we find them? And if you think about it for a second, the object that we're trying to find is not an easy one to find. It doesn't seem to produce any light. And if you're far away from it, gravity is no different than for any other object. So how can you find such an object? It looks like any other object based on its gravity, but it doesn't produce any light, so it doesn't seem like you can see it in the night sky. That's an extraordinarily difficult object to find. If you look up at the sky, as I think many of you have done, probably more often than I have, that's actually not true. To be completely honest, this is an aside, the way I got into astronomy is I grew up in a small town in upstate New York. We lived out in the country, and I got into astronomy by doing astrophotography. So that I ended up doing more theoretical things, but I got into it by looking at the sky and taking pictures. But in any case, you know, if you look up at the sky, you often see dark regions like in the right of this image here. This dark region is not a black hole. This dark region is actually just that there's some junks, what we call gas and dust, between us and the background stars, and that gas and dust blocks the light of the background stars. So finding a black hole out there in the universe is a lot harder than just looking up and finding dark regions where there isn't light in the night sky. Because the absence of light mostly means very few stars and/or there's stuff blocking the light of background stars. There are actually multiple ways that we find black holes out there in the universe. The one I want to focus on for the rest of the talk is the most astonishing, the most counterintuitive, and the most paradoxical, given everything I've just told you about the basic fundamental properties of black holes. The way we find black holes in nature, the way we have historically and still today found the most black holes out there in the universe, is that surprisingly, based on how they're defined, black holes actually produce the brightest sources of light out there in the universe. These are so why is that surprising? It's surprising because black holes are defined to be objects from within which nothing can escape. So how can they possibly produce the brightest sources of light in the universe? And I'll tell you that in a couple of minutes. These are just two examples of black holes producing extraordinarily bright sources of light. One of these is a galaxy that'll be featured prominently in the rest of the talk called M87. The M is for the Messier catalog of objects in the sky, mostly galaxies, some nebulae, as we now know. And so what you're seeing here is actually mostly in this image labeled M87, is mostly the galaxy, the billions of stars that make up the galaxy M87, but you see this funky linear feature seeming to originate from the center of the galaxy that we think is actually produced from very close to the black hole at the center of the galaxy. And then the rightmost image is a picture of a galaxy taken with the Hubble Space Telescope, where the two images show what HST, Hubble, sees sort of natively, which looks like a point source of light with these diffraction spikes. The lines in the rightmost image are not jets. They're artifacts of the image because the image looks like a point source. And then what astronomers have done is very, very, very carefully subtracted off that point source of light and seen that there's actually a galaxy at the location of that super bright source of light. And we think that super bright source of light is actually produced in the vicinity of a black hole, and that the light from near the black hole is actually outshining the trillions of stars that make up the galaxy. So how can a black hole, an object defined to not produce any light, how can it actually produce the brightest sources of light that we see in the sky? So the basic idea is that the light is not produced from inside the event horizon. It can't be. Any light produced by stuff inside the event horizon cannot get out to us, an observer far away. Instead, the light we see from black holes in the night sky is produced by gas that is outside the event horizon, only a little bit outside the event horizon. So it's gas that is about to plunge through the event horizon, but is still outside the event horizon. So that sort of solves the basic paradox. The next question is, why would that gas be so bright that it would produce some of the brightest sources of light in the universe? So the idea is illustrated in this schematic, not real artist conception image I'm showing you here. It's that if you have gas falling into a black hole, it forms a sort of whirlpool-like configuration that we call an accretion disk. This shares some similarity to your bathtub as water goes down the drain, right? It sort of swirls around the drain. Same idea for gas spiraling into a black hole. So the fundamental reason that black holes produce the brightest sources of light in the universe is that their gravity is the strongest of any object in the universe. And that means that as object spirals into a black hole, it is moving faster around a black hole than it would be around any other object in the universe, like a normal star or a galaxy, or even something weird like a white dwarf. And that gas that's moving incredibly fast at nearly the speed of light, different regions of the gas spiraling into the black hole are moving at different speeds. And when you have gas moving at different speeds, it's sort of like what happens on a cold night where you use your hands moving at different speeds. You rub your hands together. Rubbing your hands together creates friction because gas, or in this case, your hands moving at different speeds, rub against each other. It converts some of the energy of motion into heat, and that heat warms your hands in the case of a cold night. In the case of gas spiraling into a black hole, this gas moving at nearly the speed of light, moving at somewhat different speeds at different distances from the black hole, that gas gets extraordinarily hot because of the friction in the gas moving at different speeds. That extraordinarily hot gas produces light, much like friction generating a fire for any of you who have been Boy Scouts or Girl Scouts or Brownies. And it really is the same basic idea. The only difference with black holes is that the gas orbiting around them is moving incredibly fast. So the gas gets incredibly hot due to this friction, and that produces an incredibly bright source of light. So if you could move your hands at nearly the speed of light, you would produce a tremendously bright source of light that would actually melt your hands and do all kinds of other bad things to your hands. We can't in practice move our hands at nearly the speed of light, but gas moving close to a black hole naturally moves nearly at the speed of light and produces these extraordinarily bright sources of light like those that I've shown you. So that's the basic resolution of the paradox of why black holes, objects defined to produce no light, actually produce some of the brightest sources of light that we see in the sky. Many objects have gas spiraling into them. They produce sources of light, but it's black holes where gravity is the strongest, things move the fastest, and so you get the brightest sources of light. So this was really understood in the 1960s. It was understood through a combination of theory and the development of new telescopes. Radio telescopes and X-ray telescopes discovered the first black holes, although this picture of the jet emerging from M87 was first made by Curtis in about 1911 with optical telescopes, but nobody had any idea what it meant for over 50 years after that. Soon after this discovery and the realization that maybe this Einsteinian crazy idea of black holes might actually exist out there in the universe, people wanted to look closer and closer to the event horizon of a black hole and see what it would actually look like. This is an extremely difficult experiment to do. And the reason it's an extremely difficult experiment is that the event horizon of a black hole is super tiny. Remember, the event horizon of a black hole with the mass of the sun is like a few miles apart. That's much, much, much smaller than the planet the size of Jupiter or the size of the sun. And so seeing a region that small is extremely difficult. So to kind of give you a feel how we do this, I need to remind you that when we look up at the sky in astronomy, what we fundamentally measure about objects isn't their true intrinsic size. What we actually measure is the angle that they subtend on the sky. And so it's sort of like when you go to an eye doctor, right? Different letters on the screen used to test your vision, right? Different letters have different apparent sizes to you for two reasons. One is that some of the letters on the screen that I'm showing you here are different intrinsically, physically in size. And so they look like smaller angles when you look at them. But also, if you walk closer to the screen or move further away, the letters look like they have a different size. They subtend a different angle because of your distance between them. So the size of objects on the sky depends both on how close the object is to us and also how far the object is from you. So I really like this example of the Eiffel Tower, where it sort of looks like the distance between the fingers of the person is about the size of the Eiffel Tower. And that's true in terms of angles, but the actual physical distance between the person's fingers in centimeters or inches is, of course, much smaller than the size of the Eiffel Tower. The angle looks as large as the size of the Eiffel Tower because the fingers are very close to the observer, in this case, our eyes or the camera lens. So the challenge then of seeing the event horizon of a black hole is finding a black hole close to us. That makes the angles bigger intrinsically, but also a big black hole, a large mass black hole, because bigger mass black holes have bigger event horizons. And it turns out that there's two black holes out there in the universe whose event horizons are the biggest in terms of the angle on the sky. One of them is the galaxy M87 that I already introduced to you. This galaxy is about 55 million light years from us. It has a 6 million solar mass black hole. Just for comparison, that angle on the sky is about a billionth of a degree. That is extraordinarily small. Our eye can only see angles that are about an arc second big. The full moon, when you look at it in the sky, subtends an angle that's a little bit less than a degree. So what we're trying to do in measuring, looking at what is going on near the event horizon of a black hole is trying to measure an angle that is about 1 billion times smaller than the size of the full moon. And so what this corresponds to in terms of an experiment is equivalent to taking a picture from the Earth of something like a dime on the surface of the moon. And we actually don't have the ability to do that. We can't use optical telescopes like what is used to take the picture of the moon I've shown here, or the picture of M87 I've shown here. We can't take an image with enough fidelity or resolution to take a picture of a dime on the moon. So how do we do this experiment in practice? I think a reasonable guess is that NASA just spent $10 billion to launch the James Webb Space Telescope into space. That telescope has taken some of the most amazing pictures that we've ever seen. Two of those examples are shown here. One of these on the left is the Crab Nebula, which is actually a neutron star left over from the explosion of of a star about 1,000 or so years ago. It turns out that despite JWST being the biggest telescope that we've launched into space, that has taken some of the best pictures of the night sky that we've ever seen, JWST fails by about a factor of 10,000 in terms of its ability to take images that resolve small enough details to actually take a picture of what is going on near the event horizon of the biggest black holes in the night sky. So what I mean by that is the JWST mirror would need to be 10,000 times larger than it actually is to take a picture that could resolve the event horizon of a black hole. And that's obviously completely impractical. We cannot either financially or engineering-wise build a version of JWST that observes at the same wavelengths that JWST observes at, but that is 10,000 times bigger. So why is JWST not up to the task? It's not because of some error in the initial design. It's basically because of the irritating laws of physics. It turns out that for any telescope, there is a smallest angle that you can possibly measure with that telescope. And that angle is the wavelength of light that you're observing at divided by the size of the telescope. And if you just take the wavelength of light that JWST is observing at, which is microns in the infrared part of the electromagnetic spectrum, you divide it by the size of the telescope, which is about a 6-mirror diameter telescope, you conclude that the angles that JWST can measure fail by 10,000 to produce images that can see what is going on near the event horizon of a black hole. So that sounds really hopeless, right? If JWST, the most expensive telescope that's ever been launched into space, can't do the job, what possibly can? And the answer is a really beautiful, amazing, clever experimental technique that was developed soon after the development of radio astronomy, a little bit after World War II. It's a technique that's called interferometry. And it's basically a cheat. You don't build a telescope that is itself on its own big enough to resolve the event horizon by the criteria I've laid out for you here. Instead, you very, 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 very carefully combine the light from two different telescopes separated by super far distances from each other. And when you do that, the diffraction limit that you get isn't given by this formula, wavelength divided by size of telescope. It's wavelength divided by distance between telescopes. And so if you put telescopes extraordinarily far apart and you very, very carefully combine the light from those two telescopes, you can create an image that has features in it that have a resolution equivalent to a telescope with a size set by the distance between the telescopes, not the size of the telescopes. And this is very, very hard to do. You need to record every single bit of information about the light hitting the telescopes. So what I mean by that in kind of detail is light is made up of electric and magnetic fields changing in space and time, and you need to record all the information about that electric and magnetic field hitting the telescope. You store it on a hard drive, you combine those hard drives after the fact, and you create this new, better image than any individual telescope can create. And this is what a team called the Event Horizon Telescope did to create an image of what it looks like near the event horizon of a black hole. And I want to stress that the Event Horizon Telescope team is really this amazing team of scientists and engineers, mostly observational astronomers. It's hundreds of people at over 60 academic institutions in over 20 countries. And among all of those people is not me. So I'm a theorist, not an observer. not an engineer, not somebody who built telescopes. And I'm in awe of the amazing engineering and experimental effort that went into building this array of telescopes and using it to make an image of what it looks like near the event horizon of a black hole. The only quibble I have is they shouldn't have named it the Event Horizon Telescope. They should have named it the Event Horizon Telescopes, because the critical thing that makes it possible is it's not one telescope. It's this array of many telescopes literally spread across the Earth, from the South Pole to Chile, to Hawaii, to Europe, to the mainland US and Arizona, to Mexico. This is the picture of the black hole at the center of M87 that the Event Horizon Telescope team took in 2017 and released in 2018. And I want to tell you a little bit about what we think this picture tells us. So just to explain to you what we're seeing, this is radio waves, not light that we can see with our eyes. The wavelength of the light is about 1 millimeter. So that's wavelengths that are, a bit shorter than a typical radio, and a typical, radio that an old car station would have listened to, a radio station that you would have listened to in your car at home would have been tuned to. And because this is radio waves, color here doesn't mean what it means to your eye. Color to your eye means the wavelength of light. Here, color doesn't tell you anything about the wavelength of light. Instead, color just tells you how bright the source of light is. So kind of yellow or white means a very bright source of millimeter light. Orange is somewhat fainter, and black is very faint. And so what you see in this image is a sort of half donut-like feature where there's this crescent-shaped region that's very, very bright in radio waves. And then there's a central deficit of light coming from a region whose size is about the size of the event horizon. So the dashed line here is the size of the event horizon on the sky, given the distance to the black hole and given the size of the event horizon of the black hole. So how do we make sense out of this picture? How do we interpret it? Well, to do that, I'm going to kind of tell you what the theoretical predictions were prior to the observations. Because in this case, the predictions made by my group and many others, spearheaded actually by a colleague of mine at the University of Illinois named Charles Gammey, the theory had made predictions of what we expected the observations to look like. And the way we made those predictions is we did computer simulations of what would happen if you threw gas spiraling into the event horizon of a black hole. And this is an example of one of the computer simulations shown by my group. This movie is showing you how much gas is there around the event horizon as a function of time in the movie, where in this particular rendition, blue, black, purple means very little gas, yellow, orange means lots of gas. And the key thing about these computer simulations is they tell us how much gas is there everywhere around the black hole, how hot is it, how is it moving, how strong is the magnetic field. They tell you basically everything about the environment around the black hole. It's basically like a super sophisticated weather forecast for the environment of a black hole. And we can turn these computer simulations into predictions of what the region near the event horizon of the black hole would look like as seen by a distant observer. So this is an example of one of the predictions that we made prior to the Event Horizon Telescope observations. The color scheme here is chosen after the fact. I sort of changed the color scheme of the predictions to look like the color scheme of the observations, but otherwise it's basically the prediction that we made prior to the observations. So again, yellow and white mean bright source of light, black and faint mean very little light. This is the same computer simulation viewed at a different time. different computer simulation viewed at a different time. And you'll notice there's sort of similarities in all of these different results. There's this ring-like, crescent-like feature with a dark region at the center, and then less light as you go further and further away from the black. So I want to kind of end by telling you, what is it about the environment of a black hole that produces this characteristic image, and what does that tell us about the actual observations that the Event Horizon Telescope? And to do this, I have to tell you about two weird features of light when the light is produced in the environment very close to the event horizon of the black hole. So the first is the following. So imagine you have a light bulb, like a light bulb in your house or in the room you're in watching this talk. If you look at the light bulb from different directions, your everyday experience is that you basically get the same amount of light in every direction, right? That's what a light bulb does. It shines the same amount of light in every direction. Amazingly, that's actually not true if the light bulb is moving super, super fast. And what I mean by super, super fast is nearly the speed of light. So if the light bulb is moving at nearly the speed of light, it turns out that if you looked at the light bulb in a direction where it's coming towards you, you would see a much brighter light bulb than if you looked at the light bulb and it was going away from you at nearly the speed of light. The reason for this is actually due to laws of physics that you're actually somewhat familiar with from everyday experience. We'll see if this works on Zoom. I'm going to try to play an audio file. So hopefully that was a super irritating noise of a car horn. And in particular, what this is, and if you can't hear it, I apologize. I'm going to describe it in words. It's the sound of a car horn going by somebody who's listening to it. And what happens as the car horn goes by is that you hear the pitch of the car horn change. As the car horn comes towards you, the pitch is a little bit higher. It's a higher pitch, it's squeakier. And as the car horn is moving away from you, it's a lower pitch. It's more like a bass voice. And the reason for this is what's known as the Doppler effect. It's that the properties of any wave, sound waves in the case of sound, like the car horn, or light waves in the case of my light bulb analogy here, any wave's properties are modified based on how the source is moving towards you. And for light, we don't normally notice that because the source of light has to be moving at nearly the speed of light in order for the properties of the light that we see to change. But that's exactly what happens in this swirling, whirlpool of gas spiraling into a black hole. So what we think happens, and what I know happens in my computer simulations, is that the reason the left-hand part of this image looks brighter, is yellower than the right-hand part of the image, is because that's the part of the swirling whirlpool that is moving towards us at nearly the speed of light, half the speed of light or so. And so it looks brighter than the side of the swirling whirlpool that's moving away from us. So the crescent is brighter on one side than the other side because of the motion of the gas spiraling into the black hole just before it goes through the event horizon. The second feature of light that you need to know to understand the Event Horizon Telescope image is that, according to Einstein's theory of gravity, everything, including light, is actually affected by the gravity of an object like the sun of a black hole. And this was actually one of the most famous predictions of Einstein's theory of relativity. Einstein predicted that as stars pass close to the sun on the sky, their apparent position on the sky will shift due to the bending of light by the gravity of the sun. And Eddington in 1919 generated an expedition to go observe an eclipse of the sun and observe the positions of stars near the sun change during the eclipse relative to other times of year. And he confirmed Einstein's prediction that the gravity of any object causes light to bend passing near that object. For stars like the sun or objects like the Earth, that bending is very small. But for objects like a black hole, the gravity of the black hole is so strong that light produced very close to the event horizon of a black hole is bent by an extraordinary amount. In fact, light produced close to the event horizon of a black hole, the more reddish line shown in this theoretical calculation, that light is bent so much that the light produced near the black hole never makes its way to a distant observer. Instead, the light is bent and ends up falling into the black hole. And what this does is in images of black holes, it creates a deficit of light in a region a bit bigger than the event horizon in size, where the deficit of light is because the light that would have come to a distant observer is instead bent by the gravity of the black hole and ends up going into the event horizon of the black hole. And the light that does make it out is preferentially bent into this ring-like shape on the sky that produces the ring in this computer simulation that I'm showing. And so what I hope to have convinced you of is this rather remarkable fact that this amazing picture of the black hole in M87 taken by the Event Horizon Telescope, which shows this crescent-like bright region with a dark region at the center, that image actually encodes in it amazing predictions and confirmation of Einstein's theory of relativity. Both Einstein's prediction that matter moving at nearly the speed of light preferentially produces its light in the direction of its motion. So we think the bottom of the image is brighter because that's the part of the swirling whirlpool going through the event horizon that is coming towards us, while the top of the image is the part of the swirling whirlpool moving away from us. And the deficit of light at the center near the horizon, the dark region, is the bending of light predicted by Einstein's theory of general relativity, where the light is bent and actually gets absorbed by the event horizon of the black hole. The last thing I'll say is that you may have noticed that my theoretical images have a lot more detail. They have a lot more fine structure than the observations. They're sharper with more details. And the reason for that is actually the finite, albeit amazing, angular resolution of the telescope. So what I'm showing here is one of the plots from one of the Event Horizon Telescope papers. They did a bunch of computer simulations like the ones that I showed you. And the top is the computer simulated images, and the bottom runs that through the software that describes what the telescope would see. And you can see that basically the optics of the telescope blurs the image out. So we think that the intrinsic images are substantially sharper than the actual image that was observed, and probably looks something more like the simulated image on the top. And so what this suggests is that there's actually a lot of room for progress in our understanding of what the region near the event horizon of a black hole looks like, that as the telescopes get better and better, our images will get better and better. And so I think it's sort of analogous to Mars. The first images of the surface of Mars taken by Lowell look something like the upper left image here. You could see a few dark spots and a few bright spots. We now know the surface of Mars looks like the lower left image here, with these amazing dry riverbeds that tell us that there was once water there, and craters, and all kinds of other amazing details. And likewise, the top image on the right is our first picture of the region near the event horizon of the black hole. It's really just a taste of what is to come. And as the observations get better and better, we will see more and more details and actually be able to make movies like the computer simulated movie I've shown you in the lower right of what happens as gas spirals into a black hole, heats up because it's moving at nearly the speed of light, and produces these extraordinarily bright sources of light that are some of the most dramatic sources of light that we see in the sky. So thank you very much for your time. I'll end there, and I'm happy to take any questions that you might have.
Right. Thank you very much, Dr. Quataert. That was incredible. That was good. That was a really great talk. So I want to open up the questions. I actually have a question, and I'd like to start with. So you mentioned that with to get around like the resolution limit, for a space telescope, we would need a space telescope 1,000 or 10,000 times bigger than the James Webb telescope. But then you mentioned that we get around that limitation with ground-based telescopes by just using telescopes that are farther apart. If we were to launch a second James Webb telescope, say, would the limiting factor there be the transmission of data back to Earth?
Yeah, so that's a great question. So that's exactly right, that in principle, if we had two James Webb Space Telescopes and we could record all of the information about the data hitting the detectors and combine it, we could use interferometry to create better images. Now, in practice, that has really only been done in the infrared part of the electromagnetic spectrum in just the last 5 or so years on the ground. And the challenge is twofold. The basic challenge is the one that you said, which is that the wavelength of infrared light is much shorter than the wavelength of radio light. And what that means is that to record all of the information about infrared light, all of the details of the electric field, actually requires hard drives that are orders, thousands and tens of thousands of times bigger than any hard drive that we have. And so the way in practice people have done this is that it's not possible to just record the data on hard drives and then combine it later. What they do is they actually, in real time, combine the light from the two telescopes. You have two telescopes near each other. For those who know a bit about telescopes, this has been done with the Very Large Telescope, which is the European 8-meter telescopes that are in Chile in the Atacama Desert. So what you do is you basically put fiber optic cables at the detectors of the telescope. You combine the light from the two telescopes, actually 4 telescopes, in real time, and you use that to do interferometry. And so this has been done just in the last 5-10 years, but the technology is not there to do this in space yet. And so we're not at the point where we can do it in space. And so from the ground, we're also still limited then in practice by the atmosphere of the Earth, which blurs images in the infrared. But I think it's not at all out of the question that as the technology improves, we will be able to do this in space, potentially both in the radio, but also in other parts of the electromagnetic spectrum. So.
Thank you so much. We have a couple questions in on the Zoom, but we do have a question in the room. So I'll go to that first. Ask your question. Or does it all make its own?
As they want to.
And there you go.
I was just wondering the role that the Higgs field plays in black holes.
So yeah, that's a great question. So if you couldn't hear on Zoom, the question is, what role does the Higgs field play on Zoom? So just to provide some context, so one of the great breakthroughs in experimental physics in the last decade was the detection at the Large Hadron Collider of what's called the Higgs boson, which is a fundamental particle, more precisely a field whose particle manifestation is this thing called the Higgs boson. And this is one of the last great parts of the standard model of particle physics, was the sort of detection of the Higgs boson. It actually plays in sort of everything I talked about. It plays basically no role. And the reason is that everything I talked about black holes, and this actually ties into one of the questions on chat, everything I talked about black holes is sort of an Einsteinian view of black holes. So that's a theory of black holes according to general relativity. So it's a theory of black holes as if there were no theory of quantum mechanics, there were no quantum field theory, which is the theory that underpins the Higgs boson or Hawking's prediction of Hawking radiation. And so everything that we have done really in astronomy about black holes is building on this sort of Einstein view of black holes rather than a more quantum mechanical view of black holes. And so to sort of address this in the context of the question on chat as well, so the question on chat is, what is the connection of Hawking radiation to the brightness of black holes? So Hawking's prediction, which is rightly one of the most celebrated theoretical predictions in physics in the last 50 years, is that if you have a black hole sitting all by itself, no gas around it, nothing around it, in general relativity, it produces no light. That's the basic prediction of general relativity. An isolated black hole produces no light because nothing can get out. What Hawking showed in an approximate attempt to combine the theory of quantum mechanics with the theory of general relativity, not a rigorous combination of the two. We don't have a rigorous combination of quantum mechanics and general relativity, but an approximate combination that we think is good enough for the purposes of the calculation Hawking did. So we think he was right, but we don't know that because it is still an approximate calculation. What Hawking showed is that an isolated black hole with nothing around it actually produces a tiny, tiny amount of light. And when I say a tiny amount of light, I mean a truly unbelievably tiny amount of light, which is hundreds of hundreds of hundreds, and I have to speak for like another minute or two saying hundreds of billions of times fainter than the black holes that we're talking about here. So Hawking radiation produces so little light for black holes that exist, that we know exist in the universe, ones that have masses like the mass of the sun or masses that are billions of times the mass of the sun. Hawking radiation produces so little light that it is totally and completely irrelevant, and it is dwarfed entirely by the light produced by the gas spiraling into the black hole. And that's another reason that big black holes have properties that we think, to very, 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 very good approximation, we can ignore all the cool quantum mechanical stuff that Hawking taught us and focus just on the sort of general relativistic picture of black holes. But, I should say that sort of view that I've just given you is the working hypothesis of, most astronomers, but it is just a hypothesis because we don't have a complete theory of black holes that combines general relativity and quantum mechanics. And one of the great holy grails of theory and observations in this field is to try to develop and test a more complete theory of gravity. So, yeah, these are great questions. So.
Are there any other questions in the room? I know we have one on the Zoom. I want to give, yep. All right. So there's a question on the Zoom. What
Yeah,
do you think about the expansions of the Penrose diagrams? Yeah.
So this is a good question. It's about Penrose diagrams, which is Roger Penrose won the Nobel Prize in Physics 4 years ago now, along with the astronomers Reinhard Genzel and Andrea Ghez. So Reinhard Genzel and Andrea Ghez won for observations of stars orbiting the black hole at the center of our galaxy, which sort of is the best case for a black hole out there in the universe. And Penrose won for his theoretical developments of understanding the sort of mathematics and physics of black holes in general relativity. And Penrose diagrams are a way of visualizing the very complicated geometry of black holes. And one of the things that those diagrams contain in them is the possibility that you could go through a black hole and end up sort of in a different part of the universe, or maybe in a parallel universe. And this idea is actually sort of at the heart of the movie Interstellar. It is how in Interstellar they travel large distances to get to some other part of the galaxy. I think those are mathematically extremely interesting properties of general relativity that you can sort of write down self-consistent math that has these crazy seeming properties that is also related to what are called wormholes, that you can travel through time and space in various senses that are very counterintuitive. I think it's extremely unclear at this point whether that is interesting math that is not actually realizable in the universe, or whether it's interesting math that actually is realizable, and at some point we'll understand how that happens and maybe even how to do it and how it's done in practice in the universe. I think it's way too early in our experimental studies of black holes and our theoretical understanding of black holes to really be able to definitively answer this question. My guess is that it's interesting thought experiments, not actually something that you could do experimentally or test experimentally, mostly because there seem to be sort of paradoxes or contradictions. If you try to follow these ideas logically through, you run into problems that make you very, very nervous, like things like you can go back and kill yourself, which seems inconsistent. You could use a black hole to go back and kill yourself as sort of one example of this. And so, but I think, as I said, I want to be completely honest here and say that I think we don't really know. This is a very active area of research. So.
Okay. I think that is about what we have time for right now. Dr. Quataert,
there was one more question about spaghettification, which
go ahead, take it.
So spaghettification is this idea that as you fall into a black hole, you're sort of inevitably ripped apart by the gravity of the black hole. And it's the tides produced by the black hole. So just like the moon produces tides on the Earth, it distorts the shape of the Earth. As you get closer and closer to the black hole, the fact that gravity is different on your head and your feet, because they're different distances from the black hole, would stretch you apart and spaghettify you, turn you into some very elongated, extended strand. And it turns out that if the black hole has a mass like a billion times the mass of the sun, that spaghettification ripping you apart would only happen inside the event horizon. And what that means, by the way, is you could fall through the event horizon and survive. You would go through the event horizon and you would survive the process. And actually, you wouldn't notice anything all that weird. And it's only as you got closer and closer to the center that you would get ripped apart and very bad things would happen. But if you took a black hole that has a mass like the mass of the sun, this spaghettification ripping you apart would actually happen outside the event. And so the sort of the damage that a black hole does to the human body, for example, always happens, but sometimes happens outside the event horizon, sometimes happens inside the event horizon, depending on the mass of the black hole. So that's a great question.
On behalf of the club, I would really love to thank Dr. Quataert for taking the time not only to present this great talk to us, but also for taking the time to comprehensively answer our questions so well. We hope to have you back again soon. Thank you.
Sure, my pleasure. Happy to do it, and it's great to know that there are so many people also excited about the night sky and about astronomy. It really is an amazing journey, and it's amazing how much we can understand about the universe just sitting here looking up at the sky. So
Absolutely.
take care, everyone, and happy holidays.
Thank you very much.